Now that we've looked at different types of chemical reactions, it's time to consider the energy changes that occur when chemical reactions take place. Some reactions release energy, like this thermite reaction. The thermite reaction is considered an exothermic reaction. Therm meaning heat, and exo meaning out of. So in an exothermic reaction, heat is going to be given off or released. The reaction that occurs within a cold pack is an endothermic reaction. Endo meaning into, and so an endothermic reaction is going to be one that consumes heat. We can't see the energy changes taking place in either of these reactions, but what we can do is measure the changes that result from the reaction. So we'll have to distinguish between what's happening with our reactants and what's going on around our reactants. And so we need to distinguish between the system, this is the actual chemicals where the reaction is taking place, and the surroundings, which is everything outside of the system. In the system, being our actual chemicals, we know that there are changes in heat occurring, but we can't measure what's actually happening. We know that if heat is released, that's an exothermic reaction, and that if heat is absorbed, it's considered an endothermic reaction. But what we can measure is what's going on outside of the system, which we refer to as the surroundings. So if we measure an increase in temperature of the surroundings, we know that heat's been given off by the system or the chemicals, meaning that that was an exothermic reaction. And if the temperature were to decrease in the surroundings, we know that that heat was then absorbed by the system, the chemicals, in an endothermic reaction. So how does all of this work? Well, energy can be stored in chemical bonds. The stronger the bond, the more stable the bond is, the less potential energy it has. That's because lots of heat or light energy is released when very strong bonds form. That means it's going to take a lot of energy to break a strong bond. Weaker bonds, which are going to require less energy to break, are higher in potential energy. So remember, strong bonds, low potential energy, weak bonds have high potential energy. So let's take a look at the reaction for the formation of water from its constituent elements, hydrogen and oxygen. Formation reactions are pretty much always going to be exothermic. And for this reaction to proceed, we're going to have to break the bonds between these hydrogen molecules and the oxygen molecules. So the hydrogen and the oxygen molecules are going to have to absorb some form of energy, usually heat or light, which will cause them to separate, breaking their chemical bond. Now these are relatively weak, nonpolar covalent bonds, so they're going to be high in potential energy. And just as energy must be put into breaking bonds, energy is going to be released when the new bonds form. And that energy will be released in the form of heat and light. And so if we end up with products having less chemical energy than our reactants had, then we have an exothermic reaction. And a product, water, with its very polar covalent hydrogen bonds being far stronger than the nonpolar covalent bonds of our reactants, those bonds will have much lower potential energy. And we know that water is a very stable molecule. Don't forget. This is called an energy diagram with the progression of the reaction on the x-axis and the energy on the y-axis. And very simply, when the energy of the products is lower than the energy of the reactants, that means that energy has been released or given off, and it is an exothermic reaction. And remember, this activation energy is simply the energy that's required to get the reaction going. Now we'll take a closer look at an endothermic reaction. Let's take a look at the cold pack. The cold pack is designed, it's got two chambers in it. One is filled with water, and the other is filled with this ammonium nitrate crystalline solid. It's an ionic compound. The bonds are pretty strong, holding the ammonium and the nitrate together to form this solid compound. And remember, strong bonds mean low potential energy. And strong bonds are stable bonds, which means it's going to take a lot of energy to break them. So to separate this into ammonium and nitrate ions, which is what's going to happen when you break the cold pack and let the water mix with the ammonium nitrate. And so, as you can see here, the water molecules are going to have to separate the ammonium and the nitrate ions and solvate this compound, and that is an endothermic process, meaning that energy is going to need to be consumed in order for this to happen. And since energy is being consumed or taken in, if you were holding the cold pack in your hand, it's going to feel cold because the cold pack is actually absorbing the heat energy from your hand. And so if we take a look at the energy diagram for this process, we have this reactant with very low potential energy, nice stable compound with strong bonds. The activation energy, the energy to get this reaction going, is going to be pretty high. It's going to take a lot of energy to get this reactant to separate into its constituent ions. And then, as the reaction progresses, the potential energy of the products is actually much higher than what the energy of the reactant started out as, meaning that energy was absorbed and we have an endothermic process. At the beginning of the video, I mentioned the thermite reaction as being an example of an exothermic reaction, and it is extremely exothermic in that it produces heat of somewhere around 2,500 degrees Celsius. And this is also an example of a single displacement reaction, which is a redox process, which we learned about in the previous chapter. The aluminum is going to cause the iron 3 oxide to be reduced because aluminum is going to form stronger bonds with the oxygen than the iron did. And the products of this reaction are molten iron, which solidifies into solid iron, and aluminum oxide. So get yourself over to YouTube and see if you can find the thermite reaction on YouTube because it's really cool.